Good morning. In this lecture, we're going to start an introduction to the world of statistics. And statistics and probability are very much connected by the central limit theorem. So statistics is a broad field in and of itself, but the basic idea is you have an incomplete picture of some population that you're trying to study. And with that incomplete picture, you want to make your best estimate of what is true about the general population. So as an example, if you'd like to try to find the true weight of Western students, it might be impractical or impossible to weigh every single student, so you're going to weigh a small subset of those students, and then you're going to use that information to infer what the true weight is for the entire population. So if you think about it, one way that you could try to estimate the true mean mu would be to take that subset of people. You could then add up all the weights and then divide by the number of people in that sample. So if we want to estimate mu, so again, this is the true value, also called a parameter, and this is a measurement on the population. What you could do is you could use X bar, where X bar is x1 plus x2 plus xn up, divided by n, adding these guys up. So here I'm using little x bar because this is a specific measurement that I'm taking. So hopefully this seems like a good measurement for the true average or the true mean just by our knowledge of what this is, even before this class, right? This is an average. But even better, this is a good measurement because we studied that the expected value of x bar as a random variable happens to be mu. So that seems like a good measurement. Well, let's say you're trying to estimate the true mean, and let's say you get x bar equals 152. So should you run out and say, oh yeah, it's going to be 152? No, because this x bar has randomness associated with it. We know that. It has randomness associated with it. We know that because we saw that it actually has a distribution. X bar is distributed normally. So a better approach, and let me back up, that's not bad to say, oh yeah, I went out there, I measured 50 or weighed 50 students, got 152, that's my best guess. That's not bad, but we could do better. Because we not only do we know that this guy has randomness associated with it, we know its distribution. So we're going to use that information coupled with the central limit theorem to not say 152, but we're going to come up with a number or an interval, something like 152 plus 3.2. So I just pulled this number out of thin air. But we're going to get an interval. And this interval is, when we do the computation, it's not pulled out of thin air. It's going to be derived from our understanding of that guy's distribution. So if you think about it, this is way better because I'm telling you, hey, this was my best guess on a single observation, but you know what? I understand it's got randomness associated with that. I can quantify that randomness, and I'll come up with an interval. And an interval that we're going to come up with is called a confidence interval. A confidence interval. So again, you've seen these lots and lots of times. I think probably the election has probably been over by the time you guys have seen this video, but with polls, 80% of Americans are going to vote for Trump, or are going to vote for Biden, or are going to vote for whoever. If you look in the newspaper, if you look at that source, it should say, and if you look at the fine print, I'm pretty sure it almost always does, it won't just say 80%. It'll say 80% plus or minus 3% margin of error. Well, what they're talking about is actually this business here. And that would be an example of a confidence interval for a proportion. So we'll get to that, but let's focus on a confidence interval for a mean. So how are we going to come up with this confidence interval? Well, let me be very specific about what I'm looking for, and then we'll derive the confidence interval formula. So I want an interval with the following property. So I want an interval such that if I repeat my process 100 times, then 95 out of 100 intervals will capture the true mean. So I'm actually going to develop some process here so that if I constructed 100 confidence intervals using that process, that 95 of those intervals will capture the true mean. Now we have to understand that I'm never going to know whether I capture the true mean or not, because the true mean is hidden from me. In fact, if I knew the true mean, I wouldn't be doing this. I don't need statistics. But I want to come up with a process which has this probabilistic or random component so that, hey, I don't know if mine captures it or not, but I feel confident that 95 out of 100 times it will. So how am I going to do that? Well, let me make an assumption. So I'm going to assume that we know what the true population standard deviation is, and then we'll develop the process which will give us a formula to do this. Now let me say that you might say to yourself, well, wait a minute. If you're going to assume sigma, then that means you have information from the population. This is a parameter from the population. And in fact, if you know sigma, you'd have to know mu as well. So a couple of things. First off, so actually, yes, that's true, but sigma might be a good approximation that you're using based on some other population. So for example, maybe it seems reasonable that, hey, the standard deviations of weights of college students doesn't really vary at different colleges, and at some other college, yes, they actually computed this, so you're going to use that. But at the same time, hey, the average weight might differ depending on, Western super active students might be a different weight than at a different university. So that's one way of thinking about it. Another way is we're going to loosen this up so that we don't have to assume sigma, but that requires some additional knowledge that we don't have just yet. So for now, we're going to assume that we actually know sigma. Okay, so how are we going to develop this? We're going to develop this through a picture proof. So let's see. This is the distribution of x bar. We know it's normal. Okay, so I know I didn't draw any y-axis. Mu is here. Who knows where it is? Doesn't actually matter. What matters is that mu is in the center, but I just don't know what its value is. And this is interesting. I do know from the theory that x bar is normally distributed, but I have no idea what mu is. I just know it's in the middle. So I don't know which normal distribution, but I know that it's some normal distribution. So I also know that there is some value out here. Let me notate it as x bar sub 0.825 and minus x bar sub 0.825. That cuts off the top 5%. So I don't actually know what those values are, but I know they exist just by the nature of my picture. So if you buy into that, then I claim, I want to write one more thing. I want to call the distance from here to here, I want to give that a name. I'm going to call that E. So I claim that x bar plus or minus E is my 95% confidence interval. So when I'm saying my 95% confidence interval, I'm talking about this. I'm talking about an interval constructed in such a way so that if I repeat the process 100 times, 95 of them will capture the true mean. Okay, so I'm going to prove this using a very sophisticated technique. This technique involves my two fingers. So watch. Let's say my first x bar, so again I can repeat this process again. My first x bar, which I'm going to call x bar sub 1, happens to be right here. So the truth of the matter again is I can't see this picture. So when I say it's right here, I don't actually know if it's to the right of mu or to the left of mu. Let me drop it down here just so I can I'm going to draw a couple of these guys, x bar 1, x bar 2, etc. And let me convince you of something. So let me construct x bar plus e, x bar minus e with my fingers. So up to the camera, right there. So this is the distance. I'm going to add it. So the interval goes out here, and I'm going to subtract it. So this is my interval that I'm creating using x bar plus e, x bar minus e. Pause the video and answer this question. Did I just capture the true mean? So hopefully you said, oh yeah, you captured the true mean because, again, I brought this x bar down, but if you look, from here to here, mu is inside of there. Question 2, in reality, am I going to know whether I just captured my true mean or not? Answer, no. I'm never going to know if that particular interval captured the true mean, but by my picture, this one just happened to do so. Okay, let's do another one. So let's say x bar sub 2 happened to be over here. Okay, let me drop it down so I can visualize this better. And same game. Here's my e distance. Okay, so x bar sub 2 is here. And my e distance out this way. We have a second interval. Is that guy going to capture the true mean? Is that interval? So hopefully you said, no, that will not capture the true mean. And I could repeat this again and again and again and again and again and again. Pause the video and convince yourself why in this process, 95 out of 100 times, I will capture the true mean. Right, hopefully you paused the video and you said, oh, well the only way for me to capture the true mean is if my x bar sub I happens to be in this region. Because if x bar sub I is in this region, then when I add e and subtract e, I capture mu. If x bar sub I is, let's say, out here, well, when I add e and I subtract e, I'm going to miss mu. I'm going to miss mu. That sounds like I'm going to miss you, but I'm going to miss mu. When is that going to happen? That's going to happen if my x bar sub I lives from here to here. And that happens 95% of the time. And I just recognized a very bad typo that hopefully you guys caught. So I wrote 0.05 here. I meant to write 0.025. Let me say that again. 95% of the time, this will capture the true mean because from here to here is 95% of the total probability. So x bar plus or minus e does what I want. Great, except we don't know what e is. Okay, we need to find out what e is. Central limit theorem comes to the rescue. So let's see how. So z sub 0.025, again, this is that value that cuts off the top 2.5%. Z sub 0.025 is x bar sub 0.025 minus mu over sigma over root n. So a couple of things. This is the central limit theorem. Again, I'm a scientist now. I'm putting equality here because I need to do a computation. I'm not writing the limit. Technically, this is not true. Technically, this should be approximately. But we're going to say equals. And again, as n gets large enough, it's close enough, well, then z sub 0.025 times sigma over root n is x bar sub 0.025 minus mu. Look at this expression, look at your picture, pause the video. What is E? Well, hopefully you said, oh, this minus this is E. So this guy, which is unknown, minus this guy, which is unknown, is my E. Well, how does that help? Do I know sigma? I sure do, because I assumed sigma. Do I know n? Yeah, that's just my sample size. Do I know z sub 0.025? Yes, I do, because that is something that I can compute. In fact, let's do that. So this is where you go to the distr key, go to inverse norm, hit enter, and type in 0.025. Again, if I do 0.025, technically that is going to give me this negative value here. And by my picture, I should be getting a positive value, so I'll just take the opposite of that. I get minus 1.96, so it's 1.96 times sigma over root n is my E. So that tells me that a 95% confidence interval is x bar plus or minus 1.96 times sigma over root n. What does that mean? That means that if I repeat a process 100 times, again, I'll get different x bars every time, then approximately 95 of those intervals should capture the true mean. So I have confidence in my result. I'm not just giving you a single point, also known as a point estimate. I'm giving you an interval. So that's a lot of theory. The application of this is super easy. The application of this is just plug and chug. All right, so how is this plug and chug? Well, so example, let's say you want a 95% confidence interval for the true mean weight of WW students. From a sample of 50 students, you get x bar is 152. You assume that sigma is 10. Again, I'm just picking that number out of thin air. So all these numbers out of thin air. So let's compute the 95% confidence interval. That's just 152 plus or minus 1.96 times sigma, which is 10, over the square root of n, or the square root of 50. So let me write this in a couple of ways. 10 times 1 point. About to do 10 times 1.96, but I think I can do that one in my head. Divided by the square root of 50, not so much. Okay, so we get 2.77. So you can write this as 152 plus or minus 2.77. Or I want to write it in interval form because I feel like every time I teach this, people don't always see this connection. Okay, so you could write it like this, and I like this way of writing it because this shows me very clearly what my x bar is. But you could also write it like this, which I think is very nice because we can see the interval. This piece, our E, is called the margin of error. I think it's a bit of a misnomer. It's because it's not a mistake. It's just this is the probabilistic piece. This is the piece that has to do with the randomness. And let me show you guys something. I mean, if you look at this formula, there's something very intuitive here. If I want to reduce my margin of error, I mean, let's think about it. If I want to reduce the random component, can I just sample more people? Would that make sense? Right? If you sample more people, you should be able to get a tighter interval because there's less randomness there. And that's exactly what our formula shows us. Right? As n increases, E decreases. So hopefully that seems reasonable and makes sense. Okay, so this is great. This is the start. In reality, you're probably not going to know sigma. So what do we do if we don't know sigma? So what if we don't know, or maybe better language is assume sigma? Because again, in reality, you're never going to know sigma. If you know sigma, you're wasting your time doing statistics because the only way to know sigma is if you have information about the entire population. Well, let's see. In this case then, in our x bar minus mu, x bar minus mu over sigma over root n, this sigma piece appeared in that previous proof only when we were trying to come up with the margin of error. Okay, so this was what we had, and from this we were able to get a z-value. So x bar is 0.25. So now we don't know this guy. So what we're going to do is we are going to estimate it. So we'll estimate sigma. And to do so, we're going to start with this formula. This is the formula for what's called the sample variance. And sigma is going to be the square root of this thing. Now, where is this formula coming from? Well, we can't get into all of the nooks and crannies of it, but let me just point a couple of things out. So first off, if this were just n on bottom, so instead of dividing by n minus 1, if we're dividing by n, then I feel like this formula would make total sense to me as a good estimate of the variance. Why is that? Well, because it's taking the square of the distances from each value in my sample minus mu. And it's dividing by n. So in that sense, it's giving each, you could think of it, and let's ignore the minus 1 for now. You could think of it as really being this formula, which sure looks like its theoretical counterpart. Right? In other words, I'm just giving each element in my sample that I'm computing, I'm giving it a probability of 1 over n. I'm giving it equal weight. That's really what that's saying. Now, with that said, we've got this weird n minus 1 business there. And the reason that we have the n minus 1 instead of the n, I can't fully go into. You'll have to take 342 to see that. But let me tell you that with this computation, it can be shown that the expected value of s squared is sigma squared. So this guy is a random variable in its own right because the x sub i's are random, and the expected value is sigma squared. If you just have an n down there, it will be what's called a biased estimate, you're not going to get sigma squared out of that. Again, if you want to see that further, you'll have to take 342. All right, back to this. So this guy is our estimate for the true variance. This guy is our estimate for the true standard deviation. So instead of this, we're going to have x bar, so 0.025, minus mu over s over root n. So the question is, what does that picture look like? Well, this expression looks very much like this expression. And in fact, as n gets larger and larger, s is going to get closer and closer to sigma. And we know that this guy's standard normal. So this picture should look normal-ish. And as n gets larger and larger, these guys should get closer and closer to a standard normal. Each of these is called a t distribution with n minus 1 degrees of freedom. So this degree of freedom terminology is another thing that comes up a lot in 342. But let me just say this is just the nomenclature that is used to describe this guy. Each of them looks more or less like a standard normal. So maybe this is 6 degrees of freedom. And actually, I'm going to use the abbreviation that we're going to see a lot, which is just df. And again, as n increases, this guy's going to look more and more like the standard normal. And in fact, as n goes to infinity, this is going to approach the standard normal. So why are these guys squishing in this way? Well, as n gets larger and larger, there's less variability, right? If you have more information from your population, then your sample will have less variability. Let me also say that this picture looks just like this picture in terms of its shape. So the proof that we did before, where we put mu here, where we put x bar sub 0.225, et cetera, it's exactly the same proof. The only difference is that at the step where we're computing our margin of error, which again is going to be x bar sub 0.25 minus mu, it's now going to be t sub n minus 1. And actually, let me add another piece of information here. So I'm putting the degrees of freedom, and then I'm putting the probability. I've seen this done both ways. So sometimes the 0.25 here, the n minus 1 here. I like to put the n minus 1 first to articulate which distribution. So t sub n minus 1 times t sub n minus 1 comes 0.25. If I multiply that by s over root n, that will be x bar sub 0.25 minus mu, which again is my e. Nothing about the picture changes because our picture is still normal-ish. Still looks like this. So if you review the proof we did earlier, it's the same exact proof. So now our confidence interval is going to be x bar plus or minus t sub n minus 1, comma 0.025. So this guy's going to depend on n times s over root n. So this is where we don't assume sigma, which quite frankly is the more realistic scenario. So let's see that in an example. Again, the theory might be a little bit on the tougher side. The application is just plug and chug. So let's say we want a 95% confidence interval for the true mean weight. And x bar is 154. Let's say n is 50. And we get a sample standard deviation of, I don't know, 10.1. Well, in this case, we'll have 154 plus or minus a t-distribution with 49 degrees of freedom, comma 0.025, times s, 10.1, over the square root of n, which is 50. So this is the only new piece. So to get this guy, if you have a TI-84-ish, it's the DISTR key again. And you go to inverse t. And then you type in the probability first. And then type in the degrees of freedom. Okay, so n minus 1 degrees of freedom, 50 minus 1 is 49, and I'm getting a negative number, which makes sense to me because, again, the 0.825 is on this side, but I'm going to put it in as a positive number. It doesn't matter because you're going to plus and minus it anyway, but I'm getting 2.01. Let me point out that before we got 1.96. So a couple of points. First off, 2.01 is bigger than 1.96 when we did the example where we assumed sigma. So this interval is going to be wider than if we knew sigma. That makes sense to me because there's more variability going on here. With that said, come on, 2.01, 1.96, crazy close already with only 49 degrees of freedom. So I said as n approaches infinity, this guy's going to approach the standard normal, but the truth of the matter is it approaches very, very quickly. So there's not actually going to be that much of a difference between the two intervals. Okay, so that's what you do there. As a final idea, we just did this with a 95% confidence interval. You know, what if I wanted a 90% confidence interval? How much of the proof changes? Well, to keep things simpler, let me go back to the standard normal example. If we want a 90% confidence interval, the only thing that's going to change, is now I really will have 0.05 here and 0.05 here. Because I want to construct those intervals so that 90% of the time I capture the true mean. So let's see. With the 95% interval, we use z sub 0.025. With the 90% interval, we're going to use z sub 0.05. With a 99% interval, I'll give you a second, see if you can figure out the correct z sub. Well, hopefully you said z sub 0.005, because if I multiply this by 2, I'll get 0.01. So 99% would be in the middle, 0.005 here, 0.005 here, and 99% in the middle. So let's see if we can come up with a generalized formula. So for a 100 times 1 minus alpha percent confidence interval, it's a little weird. You'll see why I'm writing it like this in a minute. For a 100 times 1 minus alpha percent confidence interval, we'll use z sub blank. See if you can pause the video, take a look here, see what you put here, and then you'll see why I'm writing it as 100 times 1 minus alpha. Give that a shot. Okay, hopefully you said to get 95, alpha is 0.05. That's how you get 95 out of that. And in that case, we used half of 0.05. In the second case, with the 90%, that's going to be 100 times 1 minus 0.1. The alpha that we used here was half of 0.1. So I guess in general, for a 100 times 1 minus alpha percent, we're going to use z sub alpha over 2. And we now have the two generalized formulas that we're going to be using. So if sigma is assumed, again, assumed or known in quotes, we'll have x bar plus or minus z sub alpha over 2 times sigma over root n. Sigma is not assumed. We'll have x bar plus or minus t with sub n minus 1 comma alpha over 2 times s over root n. So these are the most generalized formulas for this lecture. Let me point out that the form or the structure of these guys are exactly the same. We have an estimate plus or minus a probability piece. And that probability piece has a distribution and an associated standard deviation. You'll see if you take future statistics classes that it's this sort of form regardless of what you're measuring. So you could be looking for a confidence interval for a mean, for a standard deviation, for a proportion, for a difference of means. It doesn't matter. It's always going to look like this in terms of its overall structure. All right, today we dove into statistics. We're trying to come up with a way to have an intelligent estimate of a true population mean. And to do so, we're using this technique of a confidence interval. Again, a confidence interval should be really thought of as coming from a process by which if you repeated the process 100 times, then 95% or some other percent of those times, you will capture the true mean. Though you'll never know whether your particular interval captured the true mean, it still gives you confidence in the process because of the underlying probability theory. So I hope you enjoyed this lecture, and I will see you next time. Thanks for listening.